Hey, Calc BC, we made it. Today we are starting lesson 6.8, the last lesson in our unit 6. This is our last two convergence tests. We're going to be learning about the ratio test and the root test today. In College Board's Unit 10, we've now, at the end of this lesson, we'll have covered all of these 10 lessons here. The next few will be covered in our next unit. You'll notice that in College Board's version of the curriculum, we only have the ratio test, but we're learning the ratio test and the root test today. The root test is one that's technically not on the AP exam, but it is so commonly part of this list of convergence tests that we're still going to learn it. And it's not that bad, so I don't feel bad about adding that extra work. But if you want the full Calc 2 experience, the root test really would be part of a Calc 2 course in college. So we are going to cover it. But you can see the College Board defines the ratio test's essential knowledge. Here it says the ratio test is a method to determine whether a series of numbers converges or diverges. And that's like all the convergence tests. So we are going to cover it, but we'll cover it in detail. So let me switch over to the notes so we can see what the ratio test really is. All right, so here are our notes, ratio and root tests. The whole first page is devoted to the ratio test. And here it is. If we have some sort of series and the series has non-zero terms, then if we check the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, and that value is less than 1, then the series converges. If that value is greater than 1, then the series diverges. Now, it's never going to be negative, right? Because we have absolute value here. But let's just think about this for a second. What we're really doing here is comparing the ratio of, some nth term and the n plus 1 term, so the next term. The next term divided by the previous term, right? And we're going to keep it general. So it's not like we're plugging in a specific value for n. We're not comparing the first and the second term or the second and the third term in the series. We're comparing just a general nth term and the next term. And if that ratio of the n plus 1 term over the n term is less than 1 as n approaches infinity, then it makes sense. You can kind of tell that the n plus 1 term would be smaller than the n term, and this ratio or this limit is telling us that that would converge. If it's greater than 1, then it's telling us that even though the terms may be getting smaller, they're approaching a value bigger than 1, so it diverges. And we're not going to dig deep into proving why this works, but it helps if you have that understanding of what you're thinking about while we're performing this test. And then number 3, if the limit equals 1, the ratio test is inconclusive. So you would need to use another test to prove convergence or divergence. All right, so let's try this. Letter A, we have this sum from n equals 1 to infinity of 2 to the n over n factorial. The ratio test is really commonly used whenever we have factorials or some combination of multiple types of terms. And really, it is common with fractions too. So here we have n factorial and 2 to the n. In letter B, you see we have some terms that are n to a power and some terms that have n in the power. So that's usually a clue that you're going to want to try to use the ratio test, just to kind of put that out there. So anyway, so for letter A, our nth term is just going to be 2 to the n over n factorial, right? We're pulling that straight from the way that the series is initially written. If I wanted to write the term for n plus 1, I'm going to be replacing every n with an n plus 1 wherever it is in the term. So it's going to be 2 to the n plus 1 over n plus 1 factorial. It's important that we use parentheses there to show that the n plus 1, whatever that sum is really what we're taking the factorial of. So now we are going to do the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Okay? And so I'll write this out once with fractions inside of fractions, and then we're just going to multiply by the reciprocal. You'll see what I mean. So we're going to do 2 to the n plus 1 over n plus 1 factorial over 2 to the n over n factorial. And so in my next step, instead of dividing by a fraction, I'm going to multiply by the reciprocal. So we still have to write the limit. It's going to be 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n, right? And so now we can multiply the numerators and multiply the denominators. So we have okay, so I'm going to do two things at once here. I'm going to see if I can find hidden in the numerator or the denominator things that are going to cancel out. So I know from properties of exponents that 2 to the n plus 1 is the same thing as 2 to the n times 2 to the 1. So I'm going to rewrite this as 2 to the n times 2 to the 1 times n factorial. And I did that because I have a 2 to the n in the denominator. I also know that n plus 1 factorial is going to be the same thing as n plus 1 times n factorial. And that is going to be helpful because then we have an n factorial in the numerator. Okay. So all I did was combine the numerators, combine the denominators because we multiplied, and I pulled out things that would be helpful to cancel out. So now let's start to cancel. So the 2 to the n's cancel and the n factorials cancel. So I'm left with the limit as n approaches infinity of what? We have a 2 left over on top and an n plus 1 left over on the bottom. And so let's think about this. As n approaches infinity, that fraction is growing. The denominator is growing. The numerator is staying as 2. So that's going to approach 0. 0, I'm pretty sure, last time I checked, is less than 1. If we look up here. So let's see. That means it converges. So that's all we have to write. 0 is less than 1. Therefore, the series n equals 1 to infinity of 2 to the n over n factorial converges by the ratio test. Okay, it is important that we show that whatever number that we get is less than 1 somehow. We don't have to necessarily write it over here with our final answer. But if you just wrote equals 0 and then say converges by ratio test, it's not really showing that you know what you're doing. So you want to definitely write your answer was less than 1, right? That's why it converges. So that means that this series we just proved does not add to infinity. It adds to some number that is finite. We just don't know what it is, but we don't need to. We just know that it converges. That was the point. Let's take a look at letter B. We're going to do the same thing. So we're going to start by defining a sub n. And a sub n plus 1. So this time I'm going to have n plus 1 squared times 3 to the n plus 1 plus 1. Right? I'm just replacing every n with n plus 1. So this is eventually going to turn into n plus 2 because I can add the ones together. But I wanted to show you that in that step so it's not confusing. And on the bottom, we're going to have 2 to the n plus 1. I'll just write it right here so that we can see exactly what's going on. This becomes n plus 1 squared times 3 to the n plus 2 over 2 to the n plus 1. Okay, so for any nth term, this is the next term. So now let's compare the ratio. So we have limit as n approaches infinity. And we are going to be doing the absolute value of a sub n plus 1 over a sub n. So I am going to skip the step this time where I wrote the fractions inside of fractions and just jump to multiplying by the reciprocal. So I'm going to have the limit as n approaches infinity of the a sub n plus 1 term, n plus 1 squared times 3 to the n plus 2 over 2 to the n plus 1 times the reciprocal of a sub n. So it's going to be 2 to the n over n squared times 3 to the n plus 1. Okay. So I'm going to do the same thing I did up here. I'm going to start to combine the numerators and combine the denominators, and I'm going to try to look for things that might be helpful to cancel out between the two. I'm going to rewrite my limit statement just like I'm doing every single time here. So I don't think anything is going to be able to cancel with the n plus 1 squared. So I'm just going to leave that the way it is. 3 to the n plus 2 and 3 to the n plus 1, that will be helpful if I pull out one of these up here. So I'm going to have 3 to the n plus 1 times 3 to the 1. Right? Because any exponent that has a sum in it, if I pull something out of it, it's multiplied with the same base. The 2 to the n is going to be stuck. And on the bottom, I have 2 to the n plus 1, so it's going to be 2 to the n times 2 to the 1 times n squared. That's not really going to be helpful. And 3 to the n plus 1, I already have that now in the numerator, so I'm going to leave it the way it is. And now you can see what's going to cancel out. The 3 to the n plus 1s cancel, the 2 to the n's cancel, and I think that is it. So let's see what we end up with here. The limit as n approaches infinity, absolute value of what, 3 times n plus 1 squared is left on top. And 2 times n squared is left on the bottom. I mean, I could go up here in a different color and actually cancel these things out so that's clear. All right, so there's that. And then, okay, so let's see if we can find this limit now that we canceled some things out. On top, I can tell that this n has a degree of 2 because if I multiplied all this out, the largest exponent would be a 2. And on the bottom, we also have a 2. So I have an Eats DC situation. The exponents are the same. So I divide the coefficients. Even after I multiply this out, the coefficient is going to be 3 on the n squared. And it's a 2 on the n squared in the denominator. So this is going to equal 3 halves as n approaches infinity. And last time I checked, 3 halves is greater than 1. According to our ratio test, if our limit is greater than 1, then the series diverges. So I'm going to write, therefore, the original series, n equals 1 to infinity, of n squared 3 to the n plus 1 over 2 to the n diverges by the ratio test. There we go. All right, let's keep going. Letter C, the sum, n plus 1 factorial over 3 to the n. So just like always, just like we've been doing, I'm going to write out a sub n and a sub n plus 1. So a sub n is n plus 1 factorial over 3 to the n. A sub n plus 1 is going to be n plus 1 factorial over 3 to the n plus 1, which I could rewrite as n plus 2 factorial over 3 to the n plus 1. So let's do this. We are going to have the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. I'm going to jump straight to where I'm multiplying by the reciprocal. So I'm going to have n plus 2 factorial over 3 to the n plus 1 times 3 to the n over n plus 1 factorial. I am going to combine the fractions and look for nice ways that things will be able to cancel. So I'm going to end up with n plus 2 times n plus 1 factorial times 3 to the n over 3 to the n times 3 to the 1 times n plus 1 factorial. And I just realized I have not been writing limit. This is, I'm glad I made that mistake because that is a pretty common issue across the board for any time that I'm doing limits. And I want to make sure to remind you that you always need to write it. So I got to go back in and write this in. Okay, so what cancels here? The 3 to the n's can cancel, and the n plus 1 factorials can cancel. So we end up with the limit as n approaches infinity of n plus 2 over 3. And I'm pretty sure that if I plug in infinity here for n, that's just going to keep growing. So that is actually going to equal infinity. And that's greater than 1. This did not say that the limit had to be, a finite number in the definition. So if it's infinity, that counts. That's greater than 1. So this we can say that this diverges by the ratio test. So we would say, therefore, the series from n equals 1 to infinity of n plus 1 factorial over 3 to the n diverges by the ratio test. All right, awesome. That is that. So if you take a look at our chart of convergence tests, we have now learned every single row on this chart. We just did the ratio test. We've also done nth term test, geometric series, p-series, direct comparison, limit comparison, alternating series, and the integral test. We know all of these tests, and everything you need to know about these tests is on this paper. On the AP exam, you will not have access to a paper like this. So these are things that you will need to know. And we're going to practice how to memorize these as we keep going. But for now, you can look at this chart. And like I said before, we are going to be looking at one more convergence test called the root test. This is not on the chart because it's not on the AP exam, but it goes hand in hand with all of these convergence tests. It's typically part of Calc 2, so we're still going to cover it. The root test is somewhat similar. We say if we take a look at the limit as n approaches infinity of the nth root of the absolute value of a sub n, if that is less than 1, then we converge, and if that's greater than 1, then we diverge, and if it equals 1, the test is inconclusive. It has all the same results as the ratio test. Really, when this is useful is pretty much only when you can make your entire term to the nth power so that some n power will cancel out with the nth root. And we can do that in letter A, so let's try it. I can say that a sub n here is e to the 2n over n to the n. Now, I don't need to worry about finding the a sub n plus 1 term because that's not part of the root test. That was only part of the ratio test. But what I would like to do is rearrange this so that the whole thing is to the nth power. So I'm going to change this numerator to e squared to the n. Now, because of properties of exponents, that's the same thing, right? 2 times n becomes 2n over here. The bottom is still going to be n to the n. And now, since the numerator and the denominator are to the nth power, I can write this as e squared over n, the quantity, to the nth power. That's really nice because when I plug it into this limit, this nth root can cancel out with this nth power. You'll see. Okay, so let's try it. So we end up with the limit as n approaches infinity of the nth root of the absolute value of a sub n. And that is going to be the limit as n approaches infinity of the nth root of the absolute value of e squared over n to the n. Now, essentially, these absolute value bars can go away because n was starting at 1 and going up. There's nothing that's ever going to make this negative in the first place. The power is definitely not going to make it negative. So the absolute value is a non-issue. We have an nth root and an nth power. So this cancels out and just leaves us with the n approaching infinity of e squared over n. And the e squared is a constant. The n is going to keep growing. So this fraction approaches 0, and that is less than 1. So we just proved by the root test that this series converges. So I'm just going to write that out. We'll have Therefore, the series n equals 1 to infinity of e to the 2n over n to the n. I'm going to write it the way that it was originally given, and that converges by the root test. Let's take a look then at letter B. Letter B is already in perfect format. It's already to the nth power. So if I wanted to list out a sub n, I'm just going to leave it the exact same way. And we can jump straight to the limit. So the limit as n approaches infinity of the nth root of the absolute value of a sub n is going to equal the limit as n approaches infinity of the nth root of the absolute value of 3n plus 4 over 2n to the n. And once again, this fraction is never going to become negative. The nth power isn't going to make it negative, so the absolute value can just be discarded, and we have an nth root of an nth power. So this becomes the limit as n approaches infinity of 3n plus 4 over 2n. Now we have a Bobo-Botten situation, and the exponents are the same, so we divide the coefficients, and we're going to get 3 halves, and 3 halves is greater than 1. So by our root test, since we have a value greater than 1, the series diverges. So we would say, therefore, the series from n equals 1 to infinity of 3n plus 4 over 2n to the nth power diverges by the root test. Okay, so that is that. We've done it. We've learned every convergence test out there that we need to know. Thank you so much for watching. Hope you enjoyed. And let me know if you have any questions on the worksheet. Thanks. Have a great day.